सर आवाज बारीक येतोय. आवाज बारीक येतोय.
बारीक येतोय. आता येतोय का आवाज?
हा, आता येतोय.
हा. Okay, this is our last chapter from the syllabus. Water requirement of crops, unit number 6. So this is the syllabus for the water requirement of crops. In that first point is the principal crops and crop season. We are going to discuss which principal crops are taken in India and which are the crop seasons in India. What is the cropping pattern in India, and what about crop rotation? What is crop rotation? That point we are going to discuss. Then next is the classes and availability of soil water. When the rainfall takes place, that water is absorbed in the soil. So what happens with this water? So that we are going to discuss. Based on the study of soil water, it is possible to find out what should be the depth of water applied for a particular crop, and what should be the frequency of watering, how many times watering is essential for a particular crop. So that calculation is possible from the study of classes and availability of soil. After that, we are going to discuss about the three terms duty, delta, and base period and their relationship in between. So these three terms are useful in order to calculate actually the crop water requirement for some command area. When we have to implement irrigation scheme for a particular area, then in that case, at first the command area is considered. After that, culturable command area is worked out. And by considering various crop seasons and principal crops over this culturable command area, then using the terms duty, delta, and base period, it is possible to calculate what is the requirement of water for crops. And from that, it is possible to find out what should be the reservoir capacity. So calculation of reservoir capacity based on crop water requirement is the main learning point in this particular chapter. So objective of this chapter is, after studying this chapter, you are able to calculate what should be the reservoir capacity based on the information of command area and based on the information of duty, delta, and base period. So this chapter is very interesting. Now, at first, we are going to discuss about what are the functions of irrigation water. So this irrigation water acts as a solvent for nutrients. These nutrients are available in the soil. So when water is absorbed by the soil, a solvent is formed, and this solution of nutrients is absorbed by the roots. So here irrigation water acts as a nutrient carrier. So the growth of the crop is not only depends on nutrients, but irrigation water is important as a nutrient carrier. Second function of irrigation water is the irrigation water supplies moisture, which is essential for the life of bacteria, beneficial to the plant growth. So that soil contains the bacteria and that needs the moisture for their growth. And these bacteria are helpful for the plant growth. They are beneficial for the plant growth. Irrigation water supplies moisture, which is also essential for the chemical action within the plant. So we know that these roots of the plant absorbs water. Along with that, they absorb the nutrients. And then the photosynthesis process takes place in which the food for the crop is prepared. So during that photosynthesis process, the chemical action takes place, and for that, this irrigation water supplies moisture. Some salts present in the soil react with this irrigation water to produce a nourishing food, and this is possible only in the presence of water. This water cools the soil and the surrounding atmosphere and thus makes it favorable for the healthy plant growth. Irrigation water with controlled supplies washes out or dilutes salt in the soil. It reduces the hazard of soil piping. Now, what is soil piping? We know what is soil piping. We have discussed it before this. And it softens the tillage pans. The tillage pan means what? It is the area, it is the field where the crops are to be grown. So it softens that tillage pan. Now, second point is types of soils. So before that, we are going to discuss about what are the functions of soil. The functions of soils are to anchor its root, then to provide water for its transpiration. Then this soil provides minerals for its nutrition, and it provides oxygen for its metabolism. So these are the functions of soil. Now we are going to discuss about the types of soils. The first classification of soil is according to the age of formation. So according to age of formation, the soil may be classified as a youthful soil, mature soil, or sensible soil. Youthful soil is a fully pervious soil and it is good for agriculture. Mature soil is a soil which is having low permeability, and sensible soil is a very hard soil and it is having almost no permeability. According to the geological process of formation, the soils are classified as residue soils. Residue soils are the soils which are formed by disintegration of rocks. So one example of residue soil is the laterite soil, which is formed due to disintegration of laterite rock. Then second is the black cotton soil. It is the residue soil of the disintegration of basalt rock. Second is the alluvial soil. Alluvial soil is a deposited soil, and it is a deposition due to the floods. Alluvial soil is also called as a deposition of waterborne materials. So in case of floods, we know that river carries lot of sediment, and these sediments get deposited along the river banks, and the soil formed along the river bank is the alluvial soil. Alluvial soil is considered as the most fertile soil. Aeolian soil is the soil which is deposited by wind action. Colluvial soil is a soil which is formed due to depositions due to rainwater at the foot of the hills. So in case of rainy season, a lot of silt flows along the hill slopes and it gets deposited at the foot of the hill, and the soil formed in such a way is called as a colluvial soil. Glacial soil is formed due to transportation and deposition of soil by glaciers. Volcanic ash is a type of soil where it is deposited due to volcanic eruption. Pan or clay pan, it is a hard layer of clay. So these are the two classifications of soil. Along with this, you know the third classification of soil, which is according to the particle size. So you are familiar with all these types. Okay, this is a classification based on particle size, coarse sand, fine sand, silt, clay, loam, loamy sand, sandy loam, silty loam, sandy clay loam, sandy clay, clay loam, silty clay loam, and silty clay. So you have studied this particular point in geotechnical engineering. Then these, and now next classification of soil is as Indian soils. So soils which are available or which are found in Indian continent, they are Indian soil. So alluvial soil we have discussed. Red soil. Red soil is formed due to disintegration of metamorphic rocks. Laterite soil is formed due to weathering of laterite rock. Black soil is formed due to weathering of basalt rock. Okay, and clay soil, sandy soils, these are the formation of all these above types of soil. Humus is a soil which is formed due to the formation, decomposition of the animals as well as the plants. So these are some of the Indian soils. Now, after studying the types of soil or classification of soil, the next point is how the land should be prepared before applying the irrigation. So our next point is preparation of land for irrigation. So when irrigation water is applied, the land should be prepared as per the following points. The first point is the land should be made clean by removing bushes and trees which are grown in that particular land. So the first point is the removal of jungle, bushes, etc. from that particular land, which is going to prepare as a land for growing the crops. Then only cleaning of the land is not sufficient. Leveling up of the land is important. So the land is made level up, and this land has given some falling gradient. We know that there are various methods of applying water to the crop. So where that water should flow under gravity, so certain falling gradient should be given to particular that plot or that particular land. If that land is big, then it should be divided into suitable plots. So based on the size of total land and based on the type of crop considered, so based on that, suitable plots can be divided. Then when the plots are prepared, then based on what is the method of applying water to the crop, the construction of supply ditches and water courses is carried out. And also the drain ditches are excavated. So we have discussed about the in control flooding methods. We know that there is a need of supply ditch, there is a need of water courses or laterals, and there is a need of drain ditch. Supply ditches supplies water to the water courses or laterals, and then excess water is diverted to the drain ditches. So there is a necessity of excavating all these ditches. Then suitable drainage arrangement should be provided for that particular land, because if proper drainage is not provided, then it may lead to the waterlogging problem. So based on this, generally a question is asked, what preparations are required? What preparations for land are required before applying irrigation water? So you have to write all these points. Okay. After this, now we are going to discuss about the classes and availability of soil. So when we consider a particular soil sample, then that soil sample consists of moisture, and that moisture is called as the soil water. And that soil water is of three types. One is hygroscopic water, second is capillary water, third is gravitational water. So first one is a hygroscopic water. So what do you mean by hygroscopic water? In geotechnical engineering, we have performed some practicals of calculation of moisture content from the soil sample. You know the procedure for that. We have collected soil sample, and that soil sample is kept in a oven for 24 hours. Okay, before that its weight is taken. Again, after 24 hours, its weight is taken, and from that we calculate the moisture content. So assume that there is one soil sample which is kept in oven for 24 hours. Now it is a complete oven dried sample. If that sample is kept in the atmosphere for next 24 hours, now already this is a oven dried sample. Now assume that it is kept in atmosphere for 24 hours. And now during these 24 hours, this oven dried sample absorbs moisture from the atmosphere. So that moisture absorbed by that particular soil sample is called as a hygroscopic water. So hygroscopic water is a very small quantity of water, and that cannot be used by humans. Next is the capillary water. So capillary water is the water in excess of hygroscopic water and which is held in the soil sample due to the molecular attraction between soil particles. So that is called as a capillary water. That capillary water is present in the soil and it can be used for the growth of the plant. So it is a useful water. Third is the gravitational water. So gravitational water is a part of soil water which drained out from that area if suitable uh, condition is available. So gravitational water is a water which is drained out from that particular soil sample. So that is called as the gravitation. Okay. So these are the three types of these are the three classes of soil: hygroscopic water, capillary water, and gravitational. So this is the sketch which shows these three classes of soil water: gravitational water, then there is the capillary water, and then hygroscopic water. So hygroscopic water is a very small amount of moisture content. Capillary water is water which is actually available for the plants, which is actually used by the plants. And gravitational water is a superfluous water which flows out from the system. Now, after studying these classes of soil water, now we are going to discuss about the soil moisture constants. Now, soil moisture constant is a moisture content. Soil moisture constant म्हणजे काय? This is a particular value of moisture content. Before going for the types of soil moisture constant, let us know about the term soil moisture tension and soil moisture stress. So first is the soil moisture tension. So first force per unit area that may be exerted to extract water from the soil is known as a soil moisture tension. And this soil moisture tension is expressed in terms of atmosphere, ATM. It is also known as a capillary potential, capillary tension, or force of suction. Soil moisture tension is also known as a force of suction because it is a force per unit area which is exerted to extract water from the soil. So that's why it is called as a force of suction, or it is called as a capillary tension or capillary potential. This soil moisture tension is inversely proportional to the moisture content in the soil, and it can be measured in the laboratory with instruments like tensometer or centrifuge. So these are the instruments used to measure the soil moisture tension. Then the next term is the soil moisture stress. So what is soil moisture stress? It is the summation of soil moisture tension and osmotic pressure of the soil solution. Soil moisture stress is what? It is the addition of soil moisture tension and osmotic pressure of soil solution. Now, what is osmotic pressure? So, osmotic pressure is increase in force caused by salt presence in soil solution. Now, see again, once again, what is soil moisture tension? It is force per unit area required to extract water from the soil. That is the soil moisture tension. And what is osmotic pressure? It is increase in that force applied per unit area. It is increase in that force which is caused by the salts present in soil solution. The salt present in soil solution provides more resistance to extract water from soil. So some additional force is required to extract that water, and that is called as the osmotic pressure. An addition of soil moisture tension and this osmotic pressure is called as a soil moisture stress. And now we are going to discuss about the soil moisture constant. So there are number of soil moisture constant. In that, the first is the saturation capacity. So what is saturation capacity? Maximum moisture holding capacity or total capacity is the amount of water required to fill all the pore spaces in soil particles by replacing all air held in pore spaces. Saturation capacity म्हणजे काय? ही एक मॅक्झिमम मॉइश्चर कंटेंट आहे. आणि हे मॉइश्चर कंटेंट मॅक्झिमम कधी होईल? When all pore spaces in the soil particles are replaced with water. Means before that there is air held in the pore spaces. So this air is removed or air is replaced by the water. So in that case, the amount of moisture content is called as a saturation capacity. So saturation capacity is the upper limit of possible moisture content. If the porosity of soil is known, the saturation capacity of soil is expressed as the equivalent centimeter of water per meter depth. That we will see what is the meaning of this particular sentence. That will be more clear to you while solving problems on this. Okay, so this is one example. So if porosity of soil, all of you are familiar with the term porosity. Porosity of soil is 50% by volume. The moisture in each meter of saturated soil is equivalent to the depth of 50 centimeter, the field space. Okay, after saturation capacity, the next soil moisture constant is the field capacity. So what is field capacity? It is the moisture content of soil after free drainage has removed most of the gravity water. Okay, so what is saturation capacity? Saturation capacity is the moisture content when in the soil sample there is a hygroscopic water, there is a capillary water, and there is a gravitational water. Okay, when three classes of soil water are available, it is called, then it is a saturation capacity. Now, what is field capacity? Field capacity is the moisture content of soil after free drainage has removed most of the gravity water. So if the gravitational water is removed from the total saturation capacity, now the moisture content is called as a field capacity. And this field capacity moisture content consists of the capillary water as well as the hygroscopic water. So this particular field capacity concept is useful for calculating amount of free water available for plants. After the field capacity, second is next moisture constant is permanent wilting point or wilting coefficient. Okay, the term is permanent wilting point. Okay, or it is also known as the wilting coefficient. Now this is a soil moisture constant. So when the moisture content reduces than the field capacity, okay, and it will reach to a certain value at which the plant can no longer extract sufficient water from the soil for its growth. So that particular moisture content is called as a permanent wilting point or wilting coefficient. Field capacity म्हणजे आपल्याला काय समजलं? There are three classes of water: gravitational water, capillary water, and hygroscopic. तर या तीन टाइप मधून जर ग्रॅव्हिटेशनल वॉटर बाजूला गेलं आणि राहिलेलं जे मॉइश्चर कंटेंट आहे ते फील्ड कपॅसिटी. विल्टिंग कोइफिशियंट किंवा परमनंट विल्टिंग पॉइंट म्हणजे काय आहे की ग्रॅव्हिटेशनल वॉटर गेलेलंच आहे प्लस कॅपिलरी वॉटर सुद्धा कमी झालेलं आहे आणि ते अशा पॉइंटला पोहोचलेलं आहे की ऍट दॅट पॉइंट प्लांट कॅन नो लॉंगर एक्सट्रॅक्ट सफिशियंट वॉटर फ्रॉम सॉइल फॉर इट्स ग्रोथ. So what is meaning of this? It is a lower end of available moisture. Okay, it is a lower end of available moisture. Now, regarding the term wilting, a plant is considered to be permanently wilted when it will not regain its turgidity even after being placed in a saturated atmosphere where little or no consumptive use of water. आता पहिल्यांदा हे लक्षात घ्या की टर्गिडिटी म्हणजे काय की जर पिकांना पाणी दिलेलं असेल तर ते व्यवस्थित उभा असते अदरवाईज ते काय होतं पीक कोमेजून जात. सो दॅट इज कॉल्ड एज लॉस ऑफ टर्गिडिटी. सो व्हेन द टर्गिडिटी विल लॉस when the moisture content is equal to wilting coefficient. When moisture content is equal to permanent wilting point. Okay, so a plant is considered to be permanently wilted when it will not regain its turgidity even after being placed in a saturated atmosphere. So that is called as a permanent wilting point. Now again we will see this particular sketch so that it will be clear to you about the soil moisture constant. So I hope now the sketch is visible to you. Okay, so this sketch is the classes of soil water. To the left here, the classes of soil water are shown. First is the gravitational water. Okay, so at the base of gravitational water, what is written here? Field capacity. When gravitational water goes out of the system, now the moisture content is called as a field capacity. When the moisture content reduces more than the field capacity peksha moisture content kami जाईल. Okay, then it will reach to the wilting coefficient. This dotted line is called as a wilting coefficient or permanent wilting point. Okay, so if the water goes below this, if the moisture content reduces below this level, then permanent wilting is possible. Okay, so that's why the capillary water, which is available from field capacity to wilting coefficient, is called as available water. Why it is called as available water? Because this particular moisture content is available for growth of the crops. Roots of the crops can take moisture from this particular category, and that's why it is called as available water. If moisture content further reduces than the wilting coefficient, in that case it is called as unavailable water. Means that water cannot be absorbed by the roots of the crops. That's why it is called as a unavailable water. Okay. So available water is a water, our moisture content available between field capacity to permanent building. Okay. And when there is a gravitational water along with the capillary water and hygroscopic water, then it is called as a saturation capacity. So saturation capacity is the first soil moisture constant we have discussed. After saturation capacity, we have discussed about field capacity. And then we have discussed about permanent wilting point or wilting coefficient. So this permanent wilting point, this particular moisture content, it depends on at what rate the water is used by plants. What is the depth of root zone? And what is the water holding capacity of soil? This permanent wilting point or wilting coefficient is higher in hot climate and it is lower in cold climate. If we measure the soil moisture tension at permanent wilting point, then it varies between 7 to 40. Wilting point is closely indicated by the moisture retained against a tension of 15 atm. Approximately, permanent wilting point can be estimated by dividing field capacity with a factor varying from 2 to 4, and that factor value depends on amount of silt in the soil. For most of the soil, wilting coefficient is about 150% of hygroscopic water. Hygroscopic water is the minimum moisture content, which is absorbed by the overnight soil sample from the atmosphere. So 150% of that is the wilting coefficient. That is a thumb rule to find out wilting coefficient if we know what is hygroscopic water. There is a point, there is a soil moisture constant which is called as a temporary wilting. Now this temporary wilting point is other than the permanent wilting point. In temporary wilting point, the crops loses its turgidity due to less moisture content, and then when the water is added, again they gain their turgidity. So that moisture content is called as a temporary wilting point. Then there is a term ultimate wilting. Ultimate wilting means what? So when the ultimate wilting of crop takes place, then it loses its turgidity permanently. So even if we add the water to the crop, it will not regain its turgidity. And ultimately here the plant will die. So that is called as the ultimate wilting. Soil moisture tension at ultimate wilting point is higher and it is up to 60 atmosphere. Ultimate wilting point occurs at hygroscopic water content, hence also recognized as a hygroscopic coefficient. So ultimate wilting is what? It is a moisture content equal to the hygroscopic water. So that's why it is called as a hygroscopic coefficient. So ultimate wilting point or hygroscopic coefficient is generally 2/3 of the permanent wilting. So based on this soil moisture constant, a short note is asked. Write note on soil moisture constant. So you have to start with saturation capacity. Second, you have to write about field capacity. Third, you have to write about the permanent wilting point. Then you have to write about temporary wilting point. Then you have to write about the ultimate wilting. So you have to write these 5 points under the answer for the note on soil moisture constant. You have to write the description for each point, and also you have to explain this with respect to the sketch shown to you, that is, which is for the classes and availability of soil water. Okay. Now there is a term available moisture. So what is available water? It is explained to you in the figure. So available moisture is the difference in water content of the soil between field capacity and permanent wilting. Okay. The difference between these two moisture content is called as available moisture. Now, out of available moisture is used for the growth of crops. But out of this total available moisture, there is some readily available moisture. And it is approximately 75% of available moisture. And it is the portion of available moisture that is most easily extracted by the plants. That is called as a readily available moisture. Now this table shows us the type of soil and different soil moisture constants, such as wilting coefficient, field capacity, and available. So now it will be clear to you from this table. Suppose for a sand, wilting coefficient is 4 and field capacity is 9. So what will be the available water? It is field capacity minus wilting coefficient. So that is 5. 9 minus 4, 5. Okay. Similarly for clay, field capacity is 35, wilting coefficient is 70. So 35 minus 17, available water is 18. Okay. There is a term moisture equivalent. So what is moisture equivalent? This is an artificial moisture property of the soil, and it is used as an index of natural property. And what is moisture equivalent? It is the percentage of moisture retained in a soil sample of wet soil 1 centimeter deep when subjected to centrifugal force of 1000 times as great as gravity, usually for a period of 30 minutes. So this is moisture equivalent. Okay. There is a term soil moisture deficiency. So what is soil moisture deficiency? Soil moisture deficiency or field moisture deficiency is water required to bring the soil moisture content of the soil up to field capacity. Now we know what is available water. It is water which is actually extracted by the plants. So higher limit of this available water is the field capacity. So due to extensive use, when this moisture content reduces, then some moisture is required to be added. So that is called as a soil moisture deficiency. Okay, so here we have completed this particular point. So today we will stop here. Again, tomorrow we will continue with this. Okay, thank you.